So we're here and we have Hubbles Law, and the idea that Hubbles Law actually, this straight line, I'll put it in perspective, Hubble's beautiful, simple math. We're going to have at least peek at some terrible math in this, is that he didn't know what he was doing, I think, at the outset, but the straightness of Hubble's line actually will tell you, or non-straightness of Hubble's line will tell you whether or not we're in one of these open-closed or critical universes. So this is what you get, and this is, at least as far as the questions in this class go, this is where we'll stop. This is like the great intellectual achievement of the 20th century. It answers all of these very fundamental questions that you had to go to some weird book to get previously. And the straightness of Hubble's law works out to Hubble's initial data set, which is about 250 million years, so 75 megaparsecs or so. So, which is to say that he was looking back in time by about 250 million years. How far back in time could you theoretically look, knowing what we know now about the age of the universe? 13.7. So, if you actually do a little bit of math, just divide those numbers, as you're asked to do on exercise 10, that's actually not a significant fraction of the distance age of the universe. But the quantitative features of it are completely not in dispute, even if you say maybe you should have looked further back in time, further away in space. The physical relic of the Big Bang exists. We believe in the Big Bang. The rest is just, in some sense, details, albeit important details. Okay, so this is what's left to fill in, the details, quote unquote, is if I take Hubble's original data and Hubble's relationship and I put it on a graph that I would need to fill to get the entire history of the universe. So this is Hubble's original data, and this goes out to 250 million years, and this would be 13 or so, 12 billion years. So this is the stuff that we don't have data on, circa 1930 or so. Do you think that line is perfectly straight from there all the way out to there? Everybody who's had to take calculus knows something about like Taylor series or something like that. It's basically local flatness for functions. If you look at a function very, very close, it always looks flat. You can get close enough. So do you guys think that Hubble's relationship is going to be this beautiful straight line all the way out to the edge of the universe? Think it's going to curve one way or another? Yeah, and that curvature is exactly the question that you need to ask if you want to know whether or not the universe is open, closed, or critical. So if it actually slows down and the the distance redshift relation actually kind of bends this way, it might tell you that, well, in the past, galaxies weren't expanding as fast as we expect them to be, therefore the universe is slowing down. If it curves up a little bit, it says, actually, things are expanding faster now than they were in the past, so we're in an open universe, and if it has, the perfect trajectory, then it's critical. So really, Hubble put all the elements in place, and we just have to do better. And the problem is we can't use the Hubble relationship to test the Hubble relationship. So you need something that's fundamentally different and can measure these absurdly long distances. And we talked about it a little bit, but this whole idea, and this is really kind of like the big project of the late 20th century in observational astronomy, I think, is the distance ladder. And we started the distance ladder with, the inability to measure parallax circa 300 BC. We finally figured that out when we got good telescopes, so people were measuring parallaxes from Earth in the, 18th century, 19th century. There are some star techniques, and we didn't talk about the pedestrian star techniques, although you can figure it out pretty quickly. We just jumped right to variables, because they're really bright, and they got us to, historically they told us that we're in one galaxy, and there are other galaxies far away. And then we jumped to redshift. And what you had to do is you had to use the parallax to calibrate the variable stars. So what Henrietta Swan-Leavitt did is she painstakingly found variable stars to which she knew the distance through parallax and established that period luminosity relationship. And then you take the variable stars, and Hubble took those to establish eventually his redshift relationship. And then there's some things in the middle, some other techniques that we could talk about, but we don't have time. What does this remind you of overall, though? So you take something, and then you use it to calibrate the next thing and the next thing and the next thing. I don't know if this is like a universal children's game, but and our kindergarten teacher was tired of listening to us. There's this game called Telephone where somebody starts a message and you whisper it in your neighbor's ear and it goes around the classroom. And what happens when it eventually gets back to you? Total nonsense, right? So this is kind of, it's one of the, it's not like a hidden shame, but it's an issue in astronomy is that you're using something to calibrate the next step and that to calibrate the next step and that to calibrate the next step. And the wonderful thing is that it's a ladder that does pull you out to the edge of the cosmos. But the bad news is if you make a mistake at any one of these rungs, the errors might propagate further on. So dark matter, we totally believe. The thing that what we're about to talk about suggests dark energy. Wait. So there will be further checks on dark energy. And so far there's only one, and it comes because of, comes at the expense of this kind of sketchy using one technique to calibrate the next. So the bottom rung of the distance ladder is parallax and laser ranging. You can actually bounce lasers off the moon. You can bounce radio waves off of Venus. So we know their distances to incredible precision. So we know how far the moon is at this point to a centimeter, right? So thermal fluctuations of the moon are observed. There's parallax. We go back and forth over the course of 2 AU from over 6 months. We see stars wobble back and forth. Compared to the background stars, we can find them. That goes out to about 300 light years very, very efficiently. Beyond that, if you work really hard. Then we've also talked about the standard rulers of spiral galaxies, where if you know spiral galaxies are all the same size, you can get really far because this isn't one star. This is 200 billion stars or so. So they're very bright, and you can see them at very large distances. They're very large rulers. They're 100,000 light years across, or 70 to 100. In the middle, there are all these things which get called standard candles, and we'll talk about them because we're about to meet the standardest of the candles, actually more like a standard bonfire or something. People, for instance, use variable stars like this thing. So it's still the GIF. There's the variable star. They're called standard candles because if you know their luminosity, then all you need to do is look at their apparent brightness to determine distance. So you have a whole bunch of candles, and they're all, they came from the same package. They're all from the same candle store. And because this one looks dimmer, I know it's actually farther apart. And the basis of that argument is that they're all the same candle. So if you work to prove something's all the same actual luminosity, then you have another way of getting out into determining distances. So for instance, Cepheid variables are a standard candle. Weirdly, you wouldn't think that a single star would give you any sort of cosmological distance scale, right? Because one star is much, much dimmer than a whole galaxy, let alone the dimmest of all the stars. It's not even really a star. And it turns out the tiny little heroes of the distance ladder story are white dwarfs, which we ran into as the remnants of solar mass evolution. So a low mass star like our sun, it'll burn to helium, then it'll puff up, become a red giant, burn helium to carbon on the red giant branch, and then blow off its outer layers in this big planetary nebula, and the thing that's left behind is a giant diamond in the sky. So something about the mass of the sun and about the size of the Earth. And they have this funny property, their electron degenerate nature, so they're just held up by the fact that you can't put two electrons in the same place. They have to stack like bricks. Is that, what do you notice about the 1 solar mass white dwarf versus the 1.3 solar mass white dwarf? Yes. So the more massive you are, the smaller you are. So this is this weird kind of, I think your book has a pillow stacking analogy, that if you start stacking really fluffy pillows on top of other really fluffy pillows, you can actually put pillows on the stack and make the whole stack compress because of the weight. So these things are actually shrinking under an increased weight of more matter on them. This cannot go on forever. And it's a pretty well-established theoretical calculation, no funny business in it, is that this stops at 1.38 solar masses. So if you nudge it over 1.38 solar masses, you have enough to, the electrons would need to be moving at the speed of light to have the appropriate degeneracy pressure. You cannot do that. It's breaking a really fundamental law of physics. So 1.39 solar masses, we're done. And fusion will start. This thing won't be able to support its own weight. This is a really old calculation from 1929 or 31 by Chandrasekhar, who basically thought about, so in an atom, right, you stack electrons in orbitals, and then you stop when you run out of electrons that are appropriate for, like, iron or gold or whatever. This is really what's going on in the electron degeneracy, is you're stacking electrons, but they're not in neutral atoms, so you're just stacking electrons through the entire star. And you can't continue to stack electrons once the electron is in such a high energy state that it's moving at the speed of light. So there is a limit, is you can't have an electron that's breaking that law. So it's really just, there's a top rung of the electron stack. And that was the basis of the calculation. So actually, you can get a close answer really easily, and then the one that Chandrasekhar did was actually pretty hard. But people have, kicked the tires on that for, it's like 90 years now almost. Yeah. Okay, so what? Well, it turns out that we see, these incredible explosions, and there are no hydrogen lines in them, so they're called type 1a supernova. The 1a just was a designation, as we don't see hydrogen. Whereas type 2 supernova, which are core collapse supernova, do have hydrogen lines in them. And this is the model of a type 1a supernova. Is 50% of stars occur in a binary pair or thereabouts. Let's say that you have, there's also finals review, let's say I have a G star and an F star. It looks kind of white to me, so we'll call it an F star. And they're in a binary pair. So who's going to die first? The F's going to die first. So the F puffs up and becomes a red giant. And, as it does so, it blows off its solar wind. Maybe it accretes a little matter onto its friend. Not really important. What does the F star leave behind? It's a solar mass-ish star. So it'll leave behind a white dwarf. And the white dwarf will just sit there merrily orbiting. It's about the same mass as it was before. A little bit less, so maybe the orbits shift. So now I have a white dwarf orbiting a G star. What's going to happen to the G star? Well, it's also a solar mass star. It just happens to have a longer lifetime than the F star. So after a couple more billion years, what's going to happen to the G star? Yeah, it's going to puff up, and it's the G star's turn to be a red giant. But now I have the puffy red star with its increased solar wind, and the white dwarf can accrete material. If that white dwarf happens to be at 1.25 solar masses and then accretes enough material to be at 1.3, 1.38, all of a sudden it hits the Chandrasekhar limit and fusion reignites. This is something that happens a lot. You actually fuse new material. But the problem is the outer layers of the star are gone. So this solar mass amount of material that's basically acting as the shielding on the nuclear reactor has all blown off. So it's just like a naked reactor core, fuses all at once, the thing goes off, burns for much less than a month. So imagine burning through like a sun's worth of fuel in about a month. It's a fairly incredibly high rate of fusion. And then maybe the other one goes away, but that's not really important. The important part is that, let's say it wasn't an F star. Let's say it was any star that you can possibly imagine. When does it blow up? So it blows up at the Chandrasekhar mass. Not half, not 5% above. It blows up at the Chandrasekhar mass. So the amount of material that I fuse is pretty standardized. And this is so this is a star. You can tell it's got the refraction spikes. This is a galaxy. You can tell it's a galaxy. This is not a foreground star. This is a star in the outskirts of this galaxy. The star and the galaxy are roughly of comparable brightness. So this is a white dwarf supernova. This is a type 1a supernova. And it basically can outshine its galaxy, or equivalent to it, for about a month. It's a very human accessible timescale. And 50% of stars occur in binaries. Well, now you guys know, if you went through the practice question, is that basically you're getting a star dying or a star coming, being born once every year or so. Basically, you get a type 1a supernova about once every century per galaxy. So it's not tremendously common, which I'm kind of grateful for, but it's common enough. And they're really bright, and they're really standardized. So this is a wonderful standard candle, and as you can see, because it's right behind next to spiral galaxies. Anywhere you can use Hubble's law, you can look at the size of a spiral galaxy. You could also use these type 1a supernova. So they're totally matched, and they go out to the farthest distant scales of the universe. So side by side, these standard hand grenades of the type 1a supernova and the galaxies of Hubble's law can both be measured. So this is a big project. They actually used computer techniques to look at these very faint, distant galaxies. I don't know if you guys saw some of the things in Galaxy Zoo. They're not beautiful pictures of the Andromeda spiral. They're like these things that kind of look like a sneeze on a windshield. So to find a type 1a supernova in that is a lot of work. So computers were definitely assisting in this project. How would you tell how do I know that this white dwarf is in this galaxy? So it doesn't have strong hydrogen lines, but it also gets redshifted, and the entire thing is redshifted. So just by the profile of the total light that's coming off of it, if this galaxy, which it isn't, but let's pretend it is, if this thing's 10 billion light years away, it's got the appropriate redshifted hydrogen lines in it. If this is 10 billion light years away, it's also had to travel. The light has had to travel for 10 billion years, and it gets redshifted too. So that tells you, totally independently of that, it's redshift tells you how far away it is. Yeah, so there's no ambiguity. It's like you don't have to calibrate it with anything else. It's like if you set off this white dwarf supernova, and then you see its overall, like its peak luminosity, but it's much smaller. That the fraction by which it's reduced tells you how far away it is, farther dimmer, basically. Okay, so now we have the thing that we were searching for, and there's other stuff in there, miscellaneous star techniques, the distance ladders, this really important, wonderful thing. But now we can get back to the first things that we can see. And what they tell us is the thing that nobody really wanted to hear. And again, you get one of these per galaxy per century. Think about the Hubble Ultra Deep Field. You got 10,000 galaxies within that field. So sure, we can see these. It's really just searching for them. They shine brightly for a month. They're very overall bright. This is another one. And so you see Hubble, 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 and then zap out to the type 1a supernova. And now we know that that line is not straight, and it's curved in the way that nobody wanted it or expected it to be curved, and this caused a bit of a stir in like 2001 or so, is that it's curved in the direction of the open accelerating universe. So there's not enough matter and energy to hold us all together, and we're flying apart, and we'll end up in the big chill or the big rip, whatever you want to call it. So, boo. Nobody wanted this. And it gets weirder, is that these are observations, but there's a law that governs how the universe is supposed to evolve. And think about it like F equals ma. Just don't kill yourself. It's like masses go in one side and then force comes out the other side. And we use that to check, for instance, the mass of galaxies and something kind of bad happened. The field equations for general relativity work the same way, as you put mass and energy in one side, and then the curvature of space and time comes out the other side. So, you measure up all the galaxies and the light and all the dark matter, put that in there too. You dump it in there, you do some calculations, and it'll tell you how the universe is supposed to curve, whether it should be open or closed or critical. So you can do this. And what you can do is we could split the world into two groups and tell me when you start, you figure out where this is going. Is let's pretend that you guys are astronomers. So all you guys actually measure the space-time curvature through your observations of type 1a supernova. And then all you guys, you calculate all the mass and the energy, and then you dump it in there and compute. Do you think that you're going to agree? Think that you ever agree in this class? So it turns out that there's a discrepancy, just like there was when we had two groups of people. Half of you pretended that you were measuring the amount of matter in a galaxy by looking at all the stars, all the luminosity, luminous matter, and half of you were like, well, just see how fast things spin, because that's really a measurement of mass too. And those two measurements of mass don't agree. It turns out if you do the same thing and you measure the total mass and energy in the universe by measuring curvature and counting it directly, you also get a wild discrepancy. And that wild discrepancy is called dark energy now. Before it was called the cosmological constant. And there was this thing, fudge factor, that Einstein put in when he first did this, which he wanted it for a different reason. He wanted the universe to have a little bit of negative curvature to overcome the fact that everything was being attracted, because he wanted to make a steady state universe that lived forever. And if everything's pulling everything else, it should collapse. But if you make the universe a little bit negatively curved, so imagine that you have, you and your buddy are on the world's most frictionless ice skates. And what's going to happen through the force of gravity? You got to wait for a while, but eventually you guys will be attracted and bump into each other. So what Einstein did originally is he put in this so-called cosmological constant to give the world a little bit of the universe a little bit of negative curvature. So now you can totally balance this curvature and the gravitational force, so everything just sits there. And he abandoned it, called it his greatest mistake. Apparently we need to resurrect this, because this is how you make sense of the fact that we don't see enough matter to make us fly apart and accelerate. It's just the totally incorrect amount of mass and energy. But according to the Type 1a supernova, we appear to be flying apart. So the equation does not work, and you need to put in this fudge factor. Okay. Any questions about that? Should have them. So this is what I'll kind of correct and post some stuff, a more careful description of it. But the important part is that GR tells you, this is the equation that we believe. All you do is you measure the mass and energy and then compute the curvature, and it doesn't work. So we can't explain the curvature that we see through the Type 1a supernova unless you put this stuff in. And it's called, because we were really uncreative, dark energy. So dark energy has peculiar properties. It's something called negative pressure. So imagine a balloon that was being pushed out, but there was no mass inside of it. And the more there is, the more it makes. So it's like kind of like a spring that actually pushes instead of pulls. So the farther you are apart, the more it pushes. It's a terrible, terrible thing. So it's going to accelerate us all to the edge of the cosmos. So this is so-called dark energy. Really, it's the name of a problem that these two observations don't agree. And if you put some, just leave that. If you put this all together, you get this chart, which you may have seen before. This is kind of scientists' belief based on the assumption that the theory of general relativity and the equations are correct, is that this is the mass and energy budget of the universe. So 4% of the universe is normal matter, things like everything that you see on the periodic table, and then neutrinos and photons, everything you've ever heard about in your life. We've already dealt with this kind of 5-to-1 ratio of dark matter to normal matter. Got that through the fact that galaxies spin too fast and interact too weirdly. And now this accelerating supernova, Type 1a supernova data, in order to make that work, you have to say that the universe is now 3-to-1 ratio of normal matter plus dark matter to dark energy. So the stuff that's trying to rip the entire universe apart, there's 3 times as much of that as everything else in the total energy budget of the universe. So this is what this pie chart comes from. Is this disturbing to anybody? So what does it do? The best description is, which isn't saying much, is negative pressure. So imagine that you have like a piston or something like that, and then you heat the bottom of the piston. The piston actually rises up, right? So the molecules inside actually get excited and they hit the top of the piston, and then the plunger actually goes up. And if you cool it down, it'll go down. So it requires mass to do that. There are little particles inside, and they're beating up the piston. Dark energy is doing that, but it's not matter. So it's just space itself hates space, and space repels space. But the problem is when space makes new space because space hates space and repels space, so you have more space, and that space hates space. Right? So this is not, right, this is very unsettling. And it's got no material properties to it. It's massless. It's just negative pressure, vacuum energy. In fact, what's weird is the particle physicists predicted that dark energy should exist, but they have too much of it by 120 orders of magnitude. It's like the great shame of particle theories. They think that, they do see this in their calculations and models, but it's too much, actually. Just by virtue of the fact that space isn't empty space. Space has vacuum energy in it. You have like a particle and an antiparticle pop out of anywhere. Okay. But this is the explanation of the picture. And I wouldn't, it's interesting at the moment, but this is 15 years old. It's predicate on one type of observation and one type of observation only. It's just predicate on the type 1a supernova. So this may be, changed. It also involves observing things that are 8 billion years, light years away. So it's one set of observations and a pretty wobbly one. Okay. But people are working on it, and again, there is this funny relationship in between both dark energy and early universe cosmology and particle physics, is that maybe what people might see at CERN is some hint about what this, kind of particle, this negative pressure stuff is. So weirdly, things like this are, in a roundabout way, investigating it. And it's a very unsettling way of ending astronomy, but honestly, this is where we are right now, is that this is like the great new thing that, the mystery of dark energy has just been opened up in the last, 15 years or so. Any questions about that? Yeah. Yeah. So, and it's annoying that they gave them such similar names. So dark matter is basically gravity without light. So it's mass, it has mass, but it just doesn't interact with electric and magnetic fields, which is really what light is. But it acts in the way that you would expect gravity to act. It attracts things. So I have two lumps of dark matter, and they'll pull each other towards each other. The dark energy is kind of the opposite. It's not mass, but it has exerts some influence on space and time, and it's repulsive. So gravity otherwise is attractive, but this vacuum energy is repulsive. It just wants to make things fly apart, actually. And if you really take this seriously, then the more you have, the more you make, and then we'll end up with the so-called Big Rip, where first galaxies will fly apart. Well, that was already happening, so that's not a big deal. But then, because the acceleration gets bigger with time, then the galaxy clusters will rip apart, then the galaxies themselves will fly apart, then the individual stars will pull apart, then the atoms, and then we'll end up as just this, kind of handful of quarks floating around the universe or something like that, if you take this very, very seriously. But I wouldn't lose too much sleep over it. I would just keep reading news about, supernova surveys. There's a new one coming out pretty soon, and then, some other way of measuring this. Yeah. Yeah, I mean, there's certainly the fun part of it. I mean, if this is correct and you came back and you happen to be born, 8 billion years from now, it'd be a very boring job as an astronomer. There would just be nothing to see. We'd all be accelerated away from everything else. It'd be maybe your galaxy, and then everything else is dark around you. This is why people don't like this idea, actually, on some level. Even after it's totally proven to be true, if it happens to be, if that happens to be the case, people will be like, I don't like it. It's a very boring universe. Nasty and boring, too. It's the worst combination. Yeah, well, the other thing is this violates a lot of deeply held notions of physics, like conservation of energy and things like that. So, yeah, nobody really knows how to feel about this, aside from it's kind of interesting. This is the inside of CERN, the particle accelerator on the Swiss-French border. And the particle accelerator ring is 30 kilometers, so you ride a bike from point to point. So couldn't really walk. It would be pretty annoying. And a human's about that big. This is one of the detectors. So maybe there's some hint about what dark energy is when you just say, I give up, I'm going to bash particles together. I don't know. They're working now. Okay, so yeah, let's go low tech from that. So I just want to really quickly wrap up what we talked about overall. Does anybody know what this is? No, it's a baboon femur. It's the Limbo Bobo, and it's the earliest known astronomical artifact. About like 28,000 years ago, found in sub-Saharan Africa, where there are these groupings of 4 times 7 kind of curved crescent-y notches. Any guesses about what it's for? 4 times 7 is 28. Crescent kind of looks like the moon. So it's actually one of the earliest, maybe, lunar calendars. So it's like this is kind of where we started. And then you have things like the Anasazi sun dagger. This is how people first got interested in astronomy. It was really just like timekeeping and rather primitive. And then at some point along the way, there came this like mystical infusion into it. I felt like doing some conspiracy theory stuff, which I always do, but we don't have time for, is the Great Pyramids are this wonderful astronomical artifact. If you correct for the precession of the Earth on its axis, go back about 4,000 years, all the sight lines in the pyramids themselves, they line up with major bright stars in Orion. Orion's a winter constellation for us, but 4,000 years ago it was a spring constellation, so it told you when to plant stuff, and the Osiris myth is a fertility myth. If you actually look at the Great Pyramids in Egypt, what do they look like? It's Orion. And then on, again, correct for the 4,000-year precession, on the equinox, they line up and make Orion's belt. So this is more than timekeeping. This is actually this kind of worshipful idea of the stars. In fact, somebody, I don't know if I believe it, but there are some claims that the pyramids were built so high because they didn't know how high up the stars were. So you climb up to the top and you can like touch the tent of the sky and grab some star stuff and live forever. That was kind of a quirky side note in history. The Greeks came up with this idea of geometry as a measure of both Earth and the heavens, and did a lot of wonderful work, like the ideas of parallax that we still use, Greek. They had pretty good measurements of the size of the Earth through suns and sight lines. Came up with this idea of, hey, triangles in space would tell us, for instance, the distance and size of the sun. Not quite right. Forgot about that for 2,000 years in Europe, at least. And this happened. So starting with Copernicus and his deathbed publication of a sun-centered model, just take a second and fathom the 1,500 years of garbage and retrograde progress in astronomy. And then from 1583 to about, Galileo's really good work was in 1610, and then Newton's 1616. So 100 years, you basically have this complete overturn of that really kind of lame backwater of Ptolemaic astronomy. And then after that, it was just kind of off to the races. We figured out that nuclear fusion powers the sun, filled out the HR diagram, found exoplanets, all of that stellar stuff. There's some terrible things out there. Supermassive black hole, dark matter, dark energy. Good news, bad news. So this actually works now. As of 6 months ago, we're detecting gravitational waves. If you want to put this thing on a timeline, so 1930s, we figured out Pluto, first proposal about dark matter and Hubbles Law, 1940s rocketry, 1970s black holes, 2010, now we have, whatever freaky Martian cult trying to get there, and dark energy was discovered in the 2000s. What do you notice about this timeline, especially compared to the Dark Ages in Europe? It's it's very compressed. And just like Galileo and Copernicus, it's kind of driven by a couple of realizations about technology. Namely, we have access to all parts of the electromagnetic spectrum and gravity waves as of a couple of months ago. And faster, yes. So the fact that you guys are in this actually kind of repeat of the Copernican Revolution, I think, because even this class in 1840 might have been a little bit dull. This isn't going to be all smooth sailing, I think. So for instance, this dark energy thing, to me sometimes it kind of reminds me of epicycles where you have a flawed theory, but you just keep trying to like, no, it works, let's fix it. But one way or another, I want to make 2 points. One is that the kind of talk about money and sending human ashes to Pluto and stuff like that and taking 10 years is that if you take NASA's entire budget from 1958 to now, it's $240 billion, not yearly, the entire budget. That's 1 month of U.S. government spending last time I was willing to feel bad enough to dig into it. So this is like what it costs to air condition army bases over the course of, a couple of years or something like that. So this is actually not a lot of money. It's like 0.25% or something like that. So you can have an Iraq war, or you can have 50 Hubble space telescopes. So just to put that in perspective, because we do throw around these big numbers. So one is it's not really that expensive. It does have a lot of positive benefits for society, I think. And now you guys know how to stay connected through citizen science programs and through news and stuff like that. And you should, because everything I say is, at least in the second half of the class, is totally under scrutiny and might be changed in the next, like 20 years or so. So, any questions? Okay. Fortunately, I can't answer them because I forgot that I'm required to do course evaluations. So if you guys wouldn't mind taking 5 minutes to do course evaluations. So the quiz is going to be online. Yeah, so open book. We just don't have enough time to do everything. So number 2, pencils. What I do want is if you guys just write on the back what was useful about the online stuff so I know what to spend time working on in the future if I do this again. And then somebody could put this, actually have a volunteer to bring this to the front office downstairs when people are done. Awesome, thank you. Thanks.
Exercise 9.
The SAM 110, so first floor right in front. Thank you.